Physics Lesson 1-1, Introduction, Units, and Uncertainty. Let's begin with some philosophy and the background that we bring to physics. Physics is the study of the rules, usually mathematical, by which the physical world operates. These rules describe how things happen. These are the laws of nature. The rules don't explain why things happen. That's because physicists are most interested in being able to predict what will happen. We have a situation, something's going to happen. Physicists want to know what will happen. Many physicists think that because they can say how things happen, they have answered the why things happen. Why does gravity pull things together? Well, Newton described the effects over 100 years before anyone asked why gravity happened. Einstein suggested that mass bends space-time. But that's just a model. It doesn't explain why. Physics deals with how. The question why is philosophy. As a Christian, I believe God created the laws of physics. Since He has made the laws, He can stop the effects of those laws when He so chooses. This is called a miracle. Many scientists think that because they can describe nature so well without using God, that it proves that God does not exist. I believe that being able to describe these intricate, interrelated laws shows the wisdom and might of God. It does allow for miracles. Furthermore, God's laws of nature don't change. Neither do His other laws, like treat others how you would like to be treated, or the 10 Commandments. Following His laws makes everything work better. Physics studies anything that can be sensed with our 5 senses. You can see it, smell it, touch it, taste it, whatever. Physics wants to study it. And as we study, we come up with 3 different levels of understanding. The first is a model. A model is a representation of something that is often too difficult or impossible to display directly. A model is only accurate under limited situations. So like this picture in the corner there is a model of an atom. Now that is very simplified. They don't really look like that. But it's useful in some situations to understand how atoms work. A theory is an explanation for patterns in nature that is supported by scientific evidence and verified multiple times by various groups of researchers. So it's not just one guy coming up with it, it's repeated over and over and over again, seems to work, but it hasn't been proven yet. A law uses concise language to describe a generalized pattern in nature that is supported by scientific evidence and repeated experiments. So a theory either may not be completely accepted by everyone. We're still doing experiments to understand it. Maybe it's for a very limited situation. A law is for the most generalized patterns and has essentially been proven. Now, the whole idea of proving things in science is difficult because you'd have to experiment in every possible situation, which can be difficult, but laws are supported time and time and time again over a very long time period. And often a law can be expressed in the form of a single mathematical equation. That's what physics likes, is to have our laws written as equations. The models, theories, and laws we devise sometimes imply the existence of objects or phenomena yet unobserved. So this can be useful to see where to study further. However, if an experiment does not verify the predictions, then the theory or law is wrong, no matter how elegant or convenient it is. If the experiments or the evidence does not back up the theory or law, then it is incorrect. For example, we're going to start off with Newtonian physics, which is physics of the everyday world. Turns out those laws and theories do not work at the microscopic scale or the very fast, high energy scale. So it's had to be modified over time as we've had new evidence. Physics uses the scientific method, which can be used to solve many types of problems. And scientific method is not just bound to science. You can use it anywhere in life to solve problems. The first step is usually observation and questioning about some phenomena to be studied. Then preliminary research is done and a hypothesis is developed. And a hypothesis is a guess as to the reason of this observation or phenomena, but we haven't really done the experiments yet. So next we have to experiment and test this hypothesis. And then you look at the results and come to a conclusion. That conclusion may be we need to test and experiment some more. Maybe it brings up a different hypothesis or whatever. So often the conclusion simply is we have to go back and study some more. So the scientific method isn't a one and done. It's very often a cycle. In order to measure things, we need units. Now there used to be all kinds of different units, such as a cable. We don't use that one much anymore. In the USA, we use the English system, used by the British Empire, hence it's sometimes called the empirical system. Or if you're buying tools, it's going to be SAE. The rest of the world uses the SI system, or the international system, or metric system. In the US, we usually call it the metric system. In the system, we have fundamental units that can only be defined by the procedure to measure them. For example, time has the fundamental unit of a second. What you see there is an atomic clock. And it turns out that certain atoms vibrate at a certain rate with current going through them. So the second is based on the time it takes for 9,192,631,770 vibrations of a cesium atom. Distance, fundamental unit, is a meter, and that is based on the distance light travels in a vacuum in 1 out of 299,792,458ths of a second. Mass is the kilogram, which used to be based on a platinum iridium cylinder kept in the Bureau of Weights and Measures near Paris, France. But they've recently redefined 1 kilogram using fundamental constants in modern physics. We also have electric current. Fundamental unit is an ampere. All other units are derived from these 4, such as a meter per second for speed. So a meter and a second combined together. The metric system uses prefixes. So we have meters, but all types of different types of meters. You could have a centimeter, a millimeter, a kilometer. Because it's based on powers of 10. So here are all the prefixes, their symbol, and the value. You should memorize those. So how do we convert units? Well, we convert units by multiplying by conversion factors so that the unwanted unit cancels out. For example, if we convert 20 gigameters to meters, start by writing the 20 gigameters. They're going to multiply by a conversion factor. And I'm going to put the gigameters on the bottom so it cancels with the gigameters on top. And then the value of giga was 10 to the 9. So we multiply straight across. So we'll have 20 times 10 to the 9 meters, and there's nothing on the bottom. And then to make this better, we're going to move our decimal over to put it into scientific notation, which will make it 2 times 10 to the 10 meters. So 20 gigameters is 2 times 10 to the 10 meters. Convert 5 centigrams to kilograms. We'll start with the 5 centigrams. I'm going to put centigrams on the bottom because I want it to cancel out. Put grams on top. The value of centi is 10 to the negative 2. Now notice the value always goes with the base unit. It went with meters, it goes with grams. It'll be not the one with the prefix, the one without the prefix. All right, but I don't want grams, I want kilograms. So I'm going to put grams on the bottom so it cancels, and kilograms on top. And kilo's value is 10 to the 3. So I'm going to put that with the base unit, the grams. Then we multiply straight across the top. I'll have 5 times 10 to the negative 2 kilograms. On the bottom, I have 10 to the 3. We can simplify that. When we divide with the same base, we subtract the exponents. So it'll be 10 to the negative 2 minus 3 kilograms, or 5 times 10 to the negative 3 kilograms. In general, whenever you go from a smaller unit to a larger unit, your number gets smaller. If you go from a larger unit to a smaller unit, your number gets bigger. As the unit changes, the number changes the opposite direction, so it stays the same value. Let's convert 25 kilometers per hour to meters per second. So we'll start with 25 kilometers. This time we have the divide, so I'm going to put the hours on the bottom. And let's convert one at a time. So let's start with the kilometers. Kilometers on top, so I'm going to put kilometers on the bottom to cancel. I'm going to go to meters. The value of kilo is 10 to the 3rd, and I put that with the base unit. Now, I have my meters. Now let's change the hours to seconds. Hours is on bottom, so I put hours on top so it cancels, and I have to think, what do I know is the number of hours? Oh, how about minutes? There are 60 minutes in 1 hour. But I don't want minutes, so I can put minutes on top to cancel with the minutes on the bottom. Have seconds. There's 60 seconds in 1 minute. Or maybe you want to remember that 1 hour is 3,600 seconds. Either way, we're going to multiply straight across. So we'll have 25 times 10 to the 3rd meters. On the bottom, we have 60 times 60 seconds. Divide that in my calculator, and I get 6.9 meters per second. Notice I had 2 digits there, So my result is going to have 2 digits. Now, all measurements we make in physics have some uncertainty. Accuracy is how close a measurement is to the correct value. Precision of a measurement, it refers to how close the different measurements are to each other. So accuracy is how close you are to what it's supposed to be. Precision is how close those measurements should be to each other. It's possible to be accurate but not precise, such as there. All the shots are close to the bullseye, but they're not close to each other. But we could be precise and not accurate. All the shots are close together, but they're not at the bullseye. The accuracy and precision of a measuring system leads to some uncertainty. Is your measuring device truly accurate? Did the end get broken off your ruler so it doesn't measure right anymore? Could still be very precise. Or if your measuring system is not very precise, how certain are you that it's going to give you the right answer? A device can repeatedly get the same measurement, so it's precise, but always be wrong, not accurate, like if you broke the end off your ruler. So just because you can always get the same answer from some way of measurement does not mean that that is the correct measurement.